We're doing inferential statistics, super fun, super exciting. Now we're not just focused on talking about the sample, we're trying to take that information that we get in the sample and apply it to the population. So when we're doing inferential statistics, we're basically dealing with probability, right? If we were to do the same study over and over, ideally we would get consistent results. If that sounds familiar, maybe it reminds you of a little thing called reliability, right? So if our measurement tool, our survey, our study is designed well enough, whatever results we get in our study should be consistent in the population. So if you have a good sample, one that represents the population accurately, the data that you get in the sample should reflect the population. Think about dating for a second, right? We've all, maybe some of us, have had a negative dating experience, and depending on when that happened in your life, if that was the first relationship that you had, you're probably going to assume that future relationships are going to be like that, right? If your first dating experience was overall average, right, and it was a relatively healthy relationship, then you're going to assume that future relationships are going to be healthy. So your initial sample, you're going to make assumptions about the population, but a bad sample can throw off your assumptions. So we have different things that we do to make sure that the information that we get from our sample is as reflective of the population as possible. So let's talk real quick about the null and research hypothesis. You are familiar with the research hypothesis, you've just never called it the research hypothesis. Your research hypothesis is just your hypothesis, right? You're assuming that there is a relationship between two variables, right? Or that there is a difference in, between two different groups. But the research hypothesis is the assumption that something has happened, right? Or will happen. The null hypothesis is the assumption that nothing will happen, that there's no relationship between two groups, right? Or between two variables. There's no difference between two groups. So I know this was cut off a little bit, but we're not actually trying to prove the research hypothesis, right? Usually we talk about trying to prove our hypothesis. Technically in statistics, we're not trying to prove our hypothesis. We're trying to see how likely it is that our null hypothesis is wrong. So you'll probably at some point hear the term reject the null hypothesis. As you're just hanging out with your friends, that might just be like, oh man, dude, you gotta totally reject the null, as your friends probably say all the time. But we are statistically, there's a chance that there's no relationship between our two variables, right? So we're trying to reject the idea that any results that we get are due to chance. So even if we find significant results in our study, it could just be because we got a weird sample, right? If we are trying to see if there's a difference between people who sit in the front row versus people who sit in the back row, I could have just happened to get a very dumb back row and a very smart front row. But in general, maybe the back row is super smart, right? So based on my sample, it could just be that the results that I got are just due to random error. So when we're doing our statistics, we're trying to reduce the chances that our results are due to error. So we're trying to reject that null hypothesis, which is just the idea that there's really no relationship between the variables that we are measuring. So I just want to give you an example of the null and research hypothesis. So let's say you were studying the relationship between the amount of time spent playing video games in hours and the amount of test anxiety that somebody might feel on an exam, right, on a 1 to 10 scale. The null hypothesis is that there is no relationship between video games and test anxiety. The research hypothesis, which would be your hypothesis, is that there is a relationship between playing video games and test anxiety. Another example, just for fun, if you were looking at the differences between people who play video games and people who don't in their levels of test anxiety, the research hypothesis, the one that you would write in your introduction section, would be that there is a difference between people who play video games and people who don't in test anxiety. The null hypothesis would be that there would be no difference between people who play video games and people who don't in levels of test anxiety. As mentioned before, sometimes when I translate it from a PowerPoint to VoiceThread, things get all jumbled together. And you know what? I'm just too lazy to fix it. I would have to go back, adjust it, re-upload it, make sure it works. And I know that you guys are just waiting to hear about inferential statistics, so I'm not going to do that to you. I'm not going to make you guys wait another moment to get this information. It's definitely all because of you and not because I just don't want to do more work. So now we're going to talk about probability sampling and statistical significance. And I promise you that I'll tell you the things that are covered up, but it's basically what's on the chart anyway. So one thing that we are concerned with is how likely is it that the results from your sample match the population, right? We want to be confident that the results that we got in our sample reflect the population. So we get to actually choose how confident we want to be. Now, the normal confidence level that you'll probably use in your study is 95%. Being 95% confident that the results that you have in your study, right, represent what's actually there in the population. Now, when talking about confidence level, you can also represent that percentage confidence in what's called an alpha level. So if you see in the chart, there's a little squiggly fish-looking thing, right? Or maybe it looks like a little alien with tiny little horns. That is an alpha. And that alpha level is just another way of representing the confidence level. The alpha level is sometimes also referred to as the p-value. So in the future, you might see the alpha level referred to as p equals. So when you set your confidence level, you're saying this is how confident we want to be that what we found in the sample exists in the population. So you set the alpha level. Now, if you're looking at this chart, you might notice something about the relationship between the confidence level and the alpha level, right? So, for example, 95, which is the more common one to use, 95%, if you represented that as a decimal, that would be 0.95. The alpha level is 0.05, right? 0.95 plus 0.05 is 100, right? Or technically 1.00, but 100%. So if you have a 90% confident interval, then your alpha level is the decimal form of 10%, because 90 plus 10 equals 100. 80, 20, right? 99.5% confidence level is an alpha of 0.005, 1/2%. You add 99 and a half plus 1/2, that is 1 or 100%. So one important thing to know is that relationship between the alpha level and the confidence level. So another thing that you want to be aware of is making the right decision. Now, there are 4 terms that I want you to be familiar with. The first two, are a true positive and a true negative. So a true positive is when you accept something that you're supposed to accept. A true negative is when you reject something that you're supposed to reject, right? So if I have uh, herpes, right, and the I go to the doctor and I give them some blood or some other fluid of mine, and the test says that I have herpes, and I have herpes. And by the way, I don't have herpes. I checked. But if I have herpes, then the test should say that I have herpes. That is a true positive. Now, I don't have herpes. So if the test said I had herpes, that would be an issue. But once again, and just to be clear, I went to the doctor, I gave them some fluids, and they said that I don't have herpes. And this is the thing, I'm going to tell you this right now, I don't have herpes. So that is a true negative, right? So if there's something that should be there and you're measuring it, the test should show that it's there. If there's nothing there, the test should show that there is nothing there, right? If your house is on fire, your fire alarm should go off, right? True positive. If your house is not on fire, then your fire alarm shouldn't go off. True negative. Now, sometimes weird things happen, right? A false positive is when you accept something that you should have rejected. So this is like getting back together with your ex. You know you shouldn't get back together with your ex. It's been 2 months. They haven't changed. But you're like, oh, it's been 2 months. They've changed. They have not, right? That is a false positive. You should have rejected them, but you totally accepted them, right? False positive. There are also false negatives. There's always a story of like the nerd who like wasn't popular, and then they became like a billionaire, and then somebody always says like, "Oh man, the people who rejected him, for some reason it's always a him, really feel should feel real terrible, right? They made the wrong decision, so they rejected that person when they should have accepted them. But also, that person probably was a jerk anyway, so probably a true negative. So we can take these and we can look at them in a variety of situations, right? So we could talk about dating. If you said yes to somebody and they are the person of your dreams and you're happy, then it's a true positive, right? If you rejected somebody because they were a serial killer, right? True negative. If or maybe college admissions, right? If a college rejects somebody who would have been a great candidate, that's a false negative. If they accept somebody who drops out 3 weeks later, right, then that would be a false positive. They accepted something that they should have rejected. Or if you are trying to like buy a car, right? So you want to buy a car that's going to be affordable in the long run. So maybe you buy a hybrid so that you can save a whole bunch of money on gas, right? Did you make the right decision? Or sorry, you want to save a whole bunch of money, hopefully by saving money on gas. But then a year later, there's an issue with the battery, right? And you have to get the battery replaced. That's $3,000. And then there are issues with the alternator, and then your rotors go out, right? And then there's another issue with the battery. And then in 3 years, it doesn't pass the smog check. So you have to take it in and out of the shop, right? So you thought that you made the right decision, right, to buy the car so you could save money, but it was actually the wrong decision. So that is a false positive. So just so you know, false positives are often called type 1 errors. False negatives are often called type 2 errors. So I introduced the idea of false positives and false negatives first, but in research methods and in a lot of statistical sciences, we refer to false positives as type 1 and false negatives as type 2. So to tie it in to our hypotheses that we were discussing earlier, we're trying to reject the null hypothesis, right? So the type 1 error is when we reject the null hypothesis. So we assume that there's a relationship between our variables, but we should have accepted the null hypothesis, right? So that's a false positive. We thought that there was a relationship, but there actually wasn't. The type 2 error is the opposite. We accept the null hypothesis. We say that there's not a relationship between our variables, but we should have actually rejected the null hypothesis. So we should have, in the population, what actually happened was that there was a relationship between our variables. Another thing to be aware of is at the end of your study, once you've gotten your results, you don't know if you've made a type 1 or type 2 error, right? The only thing that you know is that you've made a decision, but you don't know if that decision is correct or not. So if you think about like a pregnancy test, right? The stick that you pee on might say that you're pregnant, might say that you're not pregnant. That test is 99% accurate, but you don't know if it's actually accurate for another few weeks, right? If it says that you're not pregnant and then you get a little growth in your belly, then that was a type 2 error, a false negative. If it says that you are pregnant, right, and 9 months later, nothing, then that's a type 1 error, a false positive. So in your study, what you need to be aware of is you're going to get results, but you don't actually know if it reflects the population or not, right? All you know is what you got in your study, and you're making your inferences based off of that information. Got it? You good? We doing good? We doing okay? You can take a break if you want. You could grab a little water, play some video games, watch watch some TV real quick. If you're on YouTube, just look at the recommendations, see what else is up there. Maybe there's something good. Check it out. I'll see you in a bit. Or just continue on. I'm here. I'm digital. You can play me whenever. So here's just a fun little illustration about type 1 and type 2 errors, right? I always hate when there's a like clear to understand visual cue, but then a professor like will go on to explain the joke. So I'm going to do that. So if you'll notice right here, right, the man in the picture is he's not pregnant, right? You can see that he's not pregnant, right? But the doctor is saying you are pregnant. Now, the doctor made an assumption, right, based off of probably some data, but the assumption is wrong, and that's what's funny about this picture, because the man is not pregnant, right? So that would be a type 1 error. Now, over here on the right side, we actually are seeing the opposite, right? So this woman is pregnant. You can tell she's holding her stomach, right? Fun fact, babies don't actually grow in the stomach. They grow in the womb. The womb. So the doctor, and I just want you to notice that this doctor is female, because doctors can be female. If you assume that doctors could only be male, be aware of that, right? So the doctor says you're not pregnant, but very clearly, right, she is pregnant. So once again, right here, She's holding her womb. So this is a type 2 error because she said no, but she should have said you're pregnant. Any questions? I'm just going to apologize for this mess of words. Oh my god, I need to figure out a way to fix this. But not today. Not today. Uh, I'm going just I'll make sure you guys can get the PowerPoint so you can read this because maybe I feel like a little bit bad. But if you can read this, you can read anything. It's kind of like one of those magic eye puzzles where if you stare at it long enough, you can see the picture. So you just have to look at it and let your eyes lose focus. But one thing to be aware of is that the type of the scales of measurement for your independent and dependent variables affect your statistics. I mentioned this before. If you remember long, long ago when we were young, I said it's very important for you guys to know these scales of measurement because it's going to affect the type of statistical test that you use. So you kind of need to be able to look at a variable, determine whether or not it's the independent or dependent variable, right? And then from there, you will be able to figure out what the scale of measurement is and then what type of statistical test you're going to use. So at the most basic, we have the chi-square. We're not going to talk much about the chi-square, but I just want you to be aware that it exists. If you have an independent variable that is nominal, a dependent variable that is nominal. So for example, like, do you have stuffed animals in your room? Yes or no? Do you have children? Yes or no, right? I'm looking to see if there's a relationship between having stuffed animals in your room and having children. Two nominal variables. I would use a chi-square to look at the relationship between those two variables. Now, if I change that to do you have stuffed animals in your room, yes or no, and how many children do you have, right? Now, the number of children that you have is ratio. So I've gone from a chi-square to a t-test, right? Now, if you'll notice, right on the independent variable side, there's this weird thing in parentheses, two levels. Now, another way of referring to levels is referring to them as groups. In nominal, right, we have categories. It's a categorical measure. The number of categories you provide are the levels. So if I say, do you play video games? Yes or no, right? That is two choices. That means that there are two levels. If I say, do you play video games, RPGs, shooters, puzzle games, Animal Crossing, whatever that is considered, or no, I've listed five choices. So there are five levels. So if I have just two levels, then I'm going to do a t-test. So the differences between males and females in their height, right? Nominal, male or female, height ratio t-test. Now, if I say male, female, non-binary, prefer not to state, right? That is four levels. Once I have three or more levels, once I have three or more categories, then I use the ANOVA. Finally, if I have a independent variable that is interval or ratio and a dependent variable that is interval or ratio, I use the Pearson R. So if I'm looking at the relationship between weight and height, or if I'm looking at the relationship between the number of stuffed animals that you have in your room and the number of children that you have, right? Remember, whenever we're counting things, that's ratio. So two ratio measurements, Pearson R. Or if one were interval and the other were ratio, right? Depression on a scale of 1 to 10, interval, and the number of stuffed animals you have, ratio, Pearson R. And just so you guys know, if you have multiple independent variables, you can do what's called the ANOVA factorial or the multiple regression. The dependent variable for these has to be interval or ratio, but the independent variable for the ANOVA factorial is nominal. The number of levels does not matter. Or for the multiple regression, which we actually talked about in the last chapter, your independent variables have to be interval or ratio. So an example of an ANOVA factorial would be, do you play video games? Yes or no. Do you drive a car? Yes or no. Do you have children? Yes or no. And then the dependent variable, right? So we have three nominal independent variables. The dependent variable would be happiness on a scale of 1 to 10. Interval, right? So three nominal independent variables, one dependent variable that is interval, ANOVA factorial. If I want to do a multiple regression, I would need to take several independent variables that were interval or ratio and see how they affect one dependent variable, right? Which is which would be interval or ratio as well. So if I wanted to look at annual income, right? So how much money you make per year as a dependent variable, that's ratio, right? And I might want to see how three different things affect that also are interval or ratio. So I could look at the number of years you spent in school, ratio, the amount of anxiety you feel on a normal day on a scale of 1 to 10, interval, and the number of times you've traveled out of the country, interval, or sorry, ratio. You thought you got me, but you didn't. Number of times you've been out of the country, ratio, right? Three interval or ratio independent variables and how they affect one ratio dependent variable. That would be the multiple regression. Let's bring it all together with some examples, right? If you're looking at the relationship between the type of pet someone has and their level of anxiety, the independent variable is the type of pet. It's nominal, 2 levels, cat or dog. Dependent variable, anxiety, interval. So the statistical test would be the t-test, right? The research hypothesis is that there's a difference in anxiety between cat owners and dog owners. The null hypothesis is that there's not a difference in anxiety between cat owners and dog owners. Now, if I got a significant relationship in my study, it could be a true positive, or I could have committed a type 1 error, which would be a false positive. I don't know, but I could have. If I committed a type 1 error, it would have I would have said that there was a difference in anxiety between cat owners and dog owners, because that's what I would have seen in my sample, but there actually isn't one in the population, right? So I rejected the null hypothesis when I should not have, right? Now, in a type 2 error, so maybe in my study, I did not find a significant relationship between my two groups, right? Or between my variables. Now, actually, there is. The type of pet you have actually does affect your level of anxiety. So I committed a type 2 error. In my study, I found that there wasn't a difference in anxiety between cat owners and dog owners, but there was in the population. So here's another one, right? This one is just a Pearson R. So we have two different ratio variables. Our independent variable is number of doors that are in your house. Dependent variable is the hours that you work every week. That means ratio, Pearson R. Research hypothesis that there is a relationship. Null hypothesis, there is not a relationship. Type 1 error, in our study we found a relationship, but there is not a relationship in the population. Type 2 error, we found that there wasn't a relationship in our study, but there actually was one in the population. So the reason why I'm talking about the type 1 and type 2 errors is not because they happen all the time, but I want you to understand what happens if they were to happen. because just because you got a significant result in your study doesn't necessarily mean that you have definitively proved your hypothesis. It's just more support for your hypothesis. So remember, in science, we always want to keep a little bit of skepticism, even in our own work, right? We don't want to just trust that just because we did a really great job, that the results that we got are accurate to the real world. We always want to have a little bit of scientific like skepticism and just go, okay, well, this is what we found, but what could we have done wrong, right? Yes, I found a relationship, but could this relationship have just been due to chance, right? Yes, I peed on the stick. It said that I was pregnant, but is it possible that I'm not, right? Yes, I gave the doctors my, fluids, and it says that I have chlamydia. But do I have chlamydia? Yes, I do. That is a true positive. Also, side note, don't have chlamydia. So don't go spreading rumors that I have chlamydia. I was using it as an example. And then just because I like giving lots of examples, here's an example for an ANOVA, right? So the independent variable is nominal and it has 4 levels, but the dependent variable is ratio. So if you have 4 more levels of a nominal independent variable and an interval or ratio dependent variable, you got yourself an ANOVA. The research hypothesis is that there's a difference. Null hypothesis is that there's not a difference. Type 1 error, we thought there was a difference, but there actually isn't one. Type 2 error, we didn't find a difference, but there actually is one in the population. You thought we were done. I gave you 3 examples. You're like, oh, he's really winding down. No, there's something very important to be aware of. Now, we're not going to get real deep into the different formulas that you deal with when you are doing these statistics, but essentially what you do is you take all the data in your study, you put it into a statistical formula, and then that formula spits out a number, right? And that number might be something like, I don't know, 2.32, right? Now, what does 2.32 mean? Nothing. In order to figure out what that means, you have to compare it to a critical value. A critical value is basically a statistical way of saying, okay, we don't know if your results are going to reflect what's in the population. But here's a threshold, right? If your number exceeds this threshold, then we're going to say it's pretty likely that what you found in your study is going to be in the population. So that critical value is the minimum value that your statistics have to reach in order to say that you're going to reject the null hypothesis. So there are different things that affect your critical value. One is your sample size, right? The more people you have in your sample, the more likely your sample is going to reflect your population, right? If you have a population of 5,000 people and you have 2,500 people in your sample, that's a pretty representative sample. If you have 12 people in your sample, it's very likely that your sample doesn't accurately reflect the population. So your sample size relates to something called degrees of freedom, but the higher your sample size, the easier it is to show significant results. Also, your confidence level, your alpha level. As we talked about before, you get to set what your confidence level is. If you want to be 70% sure, then it's going to be much easier for you to show significant results. If you want to be 99.5% sure, the cost of that certainty is it's going to be much harder for you to get significant results. It's going to be a much higher critical value. So the other thing that affects the critical value is the presence of a tailed test, which we'll talk about in just a second. So here's a critical values graph. Now, if you'll notice, there's this red area over here, right? And right there, you'll see a 0.05. Now, 0.05, does that sound familiar to anyone? Professor, isn't that the alpha level for a confidence level of 95%? Shut up, nerd. Get out of here, you nerd. Answering questions. This wasn't even recorded the same day that you're listening to it, you nerd. Get out of here. So, yes, this is the alpha level of 0.05. So the confidence level is essentially this area over here where we're saying, okay, if the scores are within this range, right, this red range, then they've exceeded the chances of being due to chance. So think of it as you and I are going down to the basketball court to play a little one-on-one, right? It's a spread. So if I beat you by 1 point in a little b-ball, right? If I beat you by 1 point, does that mean that I'm definitely a better player than you? Maybe, right? Maybe yes, maybe no. Could be due to chance, right? I could just be having a better day than usual. Or you could be having a worse day than usual. So, how many points do I need to beat you by in order to show that I'm definitively the better player? That's what our critical value essentially is, right? We're saying if the difference between groups is this significant, right, then it's very unlikely to be due to chance. And it's just based off of how confident we want to be. 70% confidence level, I beat you by 1 point, we're pretty sure I'm a better player, right? 90% confidence level, I have to beat you by 3 points. 99% confidence level, I have to beat you by 5 points, right? To show that I'm definitively the better player. So that's what our critical values are. Now, you'll notice here that these little critical areas are on both sides. Huh. Wonder why that is. So the reason for that is this is what's called a two-tailed test. Because look right here, that is a tail. Look right here, that is a tail. The one that we looked at before was a one-tailed test. Now, if you notice something about the alpha level, now the alpha level is still 0.05. But you're looking and you're saying, Professor Thompson, I don't think you know how to read, right? And sometimes that's true. Reading is hard. There are squiggles and they're supposed to mean things. I don't get it. But if you look at these two values, 0.025, if you were to multiply it by 2, because there are 2 of them, right? Then you would get 0.05. So in a two-tailed test, you're actually splitting up the alpha level so that you can have the same level of the same confidence level, right? So if I had 0.05 on both sides, that would be problematic because then my alpha level would be 0.10, right? Which would be a confidence level of 90, not 95%. So that's the two-tailed test. So why am I bringing up two-tailed tests? What's the point of bringing them up? That's a very good question. And I'm not going to answer it. Okay, fine. I'll answer it. Depending on how you state your hypothesis, you could either have a one-tailed test or a two-tailed test. A one-tailed test is when you make a specific assumption, okay? So your normal hypothesis is, I think that there's a relationship between these two variables. That would be a Pearson R, right? You're looking to see if there's a relationship between two variables. Now, if I assume that there is a positive relationship, then the distribution has to only go on, on one side, right? Because anything that's on the negative side doesn't matter. If I just say that there's a relationship, it doesn't matter if it's a positive or a negative relationship. So if you have an assumption, right, that it's either positive or negative, then it becomes a one-tailed test. If you're just looking to see if there is a relationship and if it doesn't matter if it's positive or negative, then it's a two-tailed test. It's slightly different for the t-test. With a t-test, you're looking to see if there's a difference between two groups. So if I assume that male students and female students are going to score differently on a test that measures substance use, right? So, Molly, alcohol, weed. I assume there's going to be a difference in how they report that. Then that is a two-tailed test, because I'm not guessing who's going to outperform the other. I'm just saying I just want to see if there's a difference. Now, if I want to see specifically if males outperform female students on this test of substance use, then I'm making an assumption. So the great thing about a one-tailed test is because this alpha level isn't split, it's actually much easier to find significant relationship. When you have a two-tailed test, your critical value is going to be higher. So a two-tailed test makes it much more difficult for you to find significant results. The downside of the one-tailed test is if your results are significant but in the opposite direction, then you're still wrong. So if it actually turns out that women are the ones who are doing a lot of substance use, right? Then that would mean that I'm still wrong, because my hypothesis was that men would outperform women, right? Or if I assume that there's a positive relationship between two variables, but there's a super strong negative relationship, if I had a one-tailed test for my hypothesis, then unfortunately, I still have to accept the null hypothesis. There was an image here and it didn't upload, and I'm just real bummed about it. It wasn't that important, but very bummed. If you're drinking right now, just pour one out real quick to this image. Just pour one out real quick. If it's something that's going to stain your carpet, please don't do that, because I cannot afford to replace anyone's carpets right now. Money is tough. So when you are reporting statistics, there are some things that you want to be aware of. You need to know the type of test that you're doing. Is it a t-test? Is it an ANOVA, sometimes also called the F-test? Or is it the Pearson R? You need to know your degrees of freedom, which are a number that are related to your sample size. Whatever statistical program you're going to use is going to give you your degrees of freedom. You're not going to need to calculate that by hand or anything like that. The statistical score, so whatever statistic that you're doing, right? If you're doing the t-test, you put all those numbers into the formula, or rather the computer software puts all the numbers into the formula, and it's going to give you a number. And then you also need to know what alpha level you're starting with. So if your results are significant, then you're going to say P equals 0.05. If your alpha level is 0.05, then you're saying at the 0.05 alpha level, my results are significant. P equals 0.05. If you say P is greater than 0.05, then that means that your results are not significant at the level that you set at 0.05, right? So P equals 0.05, significant. P greater than 0.05, not significant. So here's a little hamster eating a birthday cake. Notice that the cake is as small as he is. It is a perfectly sized cake for a hamster. This hamster is having a little salad with a nice glass of wine. This hamster also enjoys playing guitar. And this hamster works for tips. Make sure to tip your hamster bartender at the end of the night because hamsters do work for tips. Don't just do the thing where you're like, $1 per drink. Sometimes you order expensive drinks. So tip your bartender, hamster well, and have a good rest of your night. Unless you're listening to this in the morning or afternoon, then when you have a night, have a good rest of it.